Hello guys, welcome back to Math Zone African Motives, still on our power machines revisions. Still on our air compressors, we talked about this, that is a direct application of our thermodynamics of gases. So you just need to apply most of the formulas there. It's just a direct application. So let us not consider wasting much time. We are going to focus with this question paper, November 2017, whereby we are given on question number 6, that was 1 kg mass of air enters a single cylinder. In this case, we are talking about a single cylinder, single stage air compressor at a pressure of. So we are given the mass that is entering, which is 1 kilogram at a pressure of, that is when it is entering. So this is our inlet pressure, which is our P1, which is 103 kilopascal in this case, and a temperature of, given our temperature to be in Kelvin. In this case, we've got 22 degrees there, so we're going to add 273 to convert to kelvins. That is going to be 295 Kelvin. All right. Then also we're given the air is then compressed after it is being compressed. All right. When it enters, it is being compressed according to the law PV to the exponent of n to a pressure of, that is the final pressure, which is P2 at 900 kilo Pascal in this case, and we are given a volume which is 1/6 of the initial. So meaning to say at the end, the final volume in this case, which is our V2, is given as 1/6 of the initial volume, that is of the initial, which is V1. So there's a relationship there between V2 and V1, depending with how are you going to use it. Ignore clearance volume, all right? Take R for air to be 0.287. All right, so this is what we are given, and R is given as 0.287 kilojoule per kg Kelvin in this case. All right. Then the question is, calculate the index, the compression index, and we are not given the compression index. Remember, this is taken or given by the law, PV to the exponent of n is equal to C. So meaning to say we are supposed to work to calculate the n there. Which part? This direct, guys, like I always say, it's an application of your gases. So if we are to consider, we have got the temperature in this case, T1, we do not have T2. We have a relationship between the volume. We've got P1, we've got P2, and here we've got a relationship between the volume between this we can write. If we cross multiply, it means V1 is going to be 6 times V2, which is 6 V2, or we can divide by 6, meaning to say V2, if we divide by 6 here, V2 is equal to V1 over 6. Or we can even create a ratio between V1 and guys, you play around this way that you want. You can even create a ratio V1 over V2. That means you divide by V2, both sides by V2. We are given that V1 over V2 is going to be 6. Or we can have in a vice versa. If you want, you can write as V2 over V1, which is going to be, this is same as over 1. So it's going to be 1 over 6. You play around that ratio the way that you want. But the question is, which part is going to consist of n? Let us check on our formula so that we can pick the best formula to what we have. In this case, we do not have all the temperatures, so it's going to be difficult for us to be working on this formula. If we had T2 and T1, then it can maybe play around with the P2 and P1, but we do not have T2 in this case. All right, we have got T1 but not T2. In terms of volume, yes, it was going to work, but here we do not have what is going to correspond. So meaning to say, the best formula that we're going to take is for pressure to volume, not for temperature, but pressure to volume. We can work with this because we are given the pressure is there. Or we can have it from here. All right, from here. We can also take it from here. If you do not want to complicate yourself, you can take it from here because this one is a simplified one. Not this one, because here we are not having any, okay? So we can take it from this one, which is simplified, or we can take it from these two that they are equal. As you can see, n minus 1 and n minus 1 will cancel. We remain with 1 over n. So you can even use that one if you want, all right? So as for me, I'm just going to take this one, which is the easier, the simplest formula here. P1 V1 is equivalent to P2 V2 to the exponent of n. So let's play around with that one and see what is going to happen. Let's play around and see what's going to happen here. So as we saw from this formula, that's P1 V1 to the exponent of n is equal to P2 V2 to the exponent of n, and we are supposed to calculate n in this case. All right. So it's either you're going to make n the subject or you're going to work with n as a single term. Because as you can see here, these two, they are related together, V1 and V2, they've got n there. So we can either divide by V1 or by V2, depending with which part do you want, all right? If you divide, whatever way that you want, guys. So here, I'm just going to remove P1 this side. So I'm going to divide by P1 this side, divide by P1 this side. So meaning I'm going to remove P1. On this side, to remove this V2 to the exponent of n, I'm supposed to divide by V2 to the exponent of n, V2 to the exponent of n. So that means this V2 to the exponent of n and this one will cancel. So I'm going to remain with V1 to the exponent of n over V2 to the exponent of n, which is same as writing as V1 over V2 to the exponent of n like this. All right. So this whole part is going to give us what at the end? Here we cancel this. We're going to remain with P1, P2 over P1. So this is going to give us P2 over P1. At least we can play around with this formula because we have a relationship that is there between V1 and V2. Remember, I said you can write this as V1 over V2 or V2 over V1. According to V1 over V2, it's 6 over 1, according to that ratio that you're given. So it means 6 over 1 to the exponent of n should be equal to P2 over P1. So our P2, in this case, we are going to take the value that is corresponding to P2 in this case, which is 900, P1, which is 103. So it's going to be 900 over 103. That's it. That's it. Just like that. We can play around. Remember, 6 over 1 is same as 6. So this is same as 6. So you are back to your mathematics. This is no longer about power machines. You're now back to N3 mathematics, calculating logarithmic or exponential equations. So this is same as 6 to the exponent of n is 900 over 103. So how do you remove the exponent of n? You introduce the logarithms in this case. So you can introduce a log or a ln like this or a direct log. It's up to you, all right? So in this case, I'm just going to introduce a log. So a log here, a log here. The moment I introduce a log, I'm going to drop this exponent. So it is going to be written as n, the logarithm of 6, which is equal to, this is now a single term. So you're now having logarithm of 900 over 103, all this as a single term. So as you can see, to find n, we can simply divide by the log of 6, all right? So guys, this is our mathematics pattern. So you can just divide by log of 6 here, by the log of 6 here. So this will cancel. So n is going to be, take note here, please use a calculator proper, this on top of the numerator. All right, so you're going to place this on top of the numerator. So it means our n at the end was going to give us something like 1,209,79 and so forth. So 1, 2, 3. This one is going to change. A 10 gives us a 1 here. So it's going to be approximately, we are going to have 1,21. So this is going to round off to a 1. So that is going to be the value of n, which is 1,21 in this case. So that's it. Then we move on to the other part. Now they need us to calculate the absolute temperature compression, which means after the compression has taken place. Remember, this is after a compression has taken place from T1 to T2. So they need us to calculate T2 after the compression. So we can choose a lot of formulas to apply here. Remember, I talked about this formula that we couldn't manage to use because we do not have T2 previously here. So you can use this formula that we are given. You can relate to any of these two. You can relate to pressure, to volume. So let me write these formulas because we are saying this part here can be equal to this, or it can be equal to this. So let's write them separately. So in terms of pressure, we saw that T2 over T1. Let us just have our formulas here. So this is 6.2. In terms of the pressure, we saw that T2 over T1 is equal to P2 over P1 to the exponent of n minus 1 over n. Then in terms of volume, we saw that the same T2 that we are supposed to focus with over T1, in terms of volume, it was given as V1 over V2 to the exponent of n minus 1. So like I said, you can use any formula to find T2 in this case. If you use this one, you can multiply by T1 here. It means T2 is going to be T1 into P2 over P1 to the exponent of n minus 1 over n. If we are to use this, multiply here by T1, it means T2 is going to be equal to T1 into V1 over V2 to the exponent of n minus 1. So you can use any comfortable formula from this part. So that's T2 is equal to T1. T1 in this case is from this information. T1 is 295. So that's 295 here. All right. Into P2 over P1. So we've got P2, which is P2 900, P1 103. So it's going to be 900 over 103 to the exponent of n minus 1. So the n is the one that we calculated here, which is 1,21. So it's going to be 1,21 minus 1 over 1,21. So that's it. We are going to obtain our T2 in this case. If you are to use this formula, you are going to obtain your T2 as 429,7406, and so forth, which is going to be 4,1 in Kelvin in this case. So that will be our T2. But now if we are to consider this formula, it means our T2 at the end was going to be T1, which is our T1 still 295. But now we are supposed to use V1 over V2 as per our ratio. And we talked about this, that we can write as V1 over V2 or V2 over V1. So we need V1 over V2, which is 6 over 1. So this would be 6 over 1. In place of V1 over V2 is going to be 6 over 1 to the exponent of n. Remember, our n was 1,21 minus 1. All right. So that's it. We are going to obtain our T2, but this time you are going to obtain something like 429,7681, which is 767 and so on. So it's going to be 768 in Kelvin like this. So as you can see, it's just these two values which are not corresponding, but the rest are fine. So any answer there is correct depending with the formula that you have worked with in this case. All right. So that was our 6.2, calculating the final or calculating the compression temperature, the absolute temperature compression, and it was 3 marks for that. All right. Then 6.3. Now to calculate the volume after compression, which is V2 after compression. We talked of a formula that here V2, there you can use any formula there. We now have T2, we have got P2, we have got the mass, we have got the R there representing the gas constant. So meaning to say we can even relate to this formula for PV, to the PV in this case, that's 6.3. If we relate from our formula, PV is equal to MRT. So this part can help us to calculate the volume. Here we've got V1 and V2, so it's not gonna work. So you can relate here that PV here on this formula is equal to MRT. So if this is P1, this is gonna be V1 T1. All right. If you're talking about P2, it's gonna be P2 V2 T2. So in this case, we need to calculate the mass. We have V1. We are supposed to calculate V2. So we are going to use it as P2 V2 M2, since we have to calculate V2. All right. So that's it. Let us see our formula, how it is going to end up. Are we going to end up with our formula? So it's said P2, V2 will be equal to MRT2, and we have to calculate the mass in this case. Sorry, the volume, which is our V2 in this case. Remember, our question here is to calculate the volume after compression, which is V2. So meaning to say, we can make V2 the subject. Yes, we can just make our V2 to be the subject by dividing here by P2 both sides. All right, so that's it. So that means at the end, we're gonna have our V2 as MRT2 over P2, which means our V2 is going to be the mass. Remember, the mass there is taken per 1 kg. We are told that the mass there is 1 kg. Here, mass 1 kg. And R here, there is 0.287. So we have got 1 kg times 0.287 times T2. So for T2 now, remember, you have got different values that you consider. If you worked with the first one, this formula, you are going to use this value as it is. If you used this one for volume, use the value that you obtained, all right? So yeah, I'm not going to use all the values. I'm just going to use the first one. But if you use this value, substitute this value in terms of your T2, all right? So in this case, my T2 is going to be 427.741, all right? 429, all right? 429, sorry. So it's going to be 429.741. All right, so that's my T2 over the pressure to, in this case, P2, which was 900 in this case, all right? So P2, you are given 900. So that was going to give us the volume at the exit, or the volume that V2, which is going to be 0.137039, which is 0.137 in cubic meters. So our volume in cubic meters in this case, all right? All right, so that's it. I think this one is direct application of our gas laws. And 6.4, the work done per kg of air. So we are supposed to calculate the work done. Considering what we've got, all right, let us check the formulas that are appropriate for the work done so that I can explain from there. So in this case, we are supposed to calculate the work done, all right? So that's 6.4. This is work done per kg. Remember, they are saying work done per kg fuel in this case, all right? We need to say we are taking our mass at a kg. All right, so let us consider our formulas on this other page here. I want you to see what we are going to do on our formula now. Remember, we talked about this work done previously, which is the power, where we calculated power when this is in cubic meters per second. We calculate the power from there. But in this case, we are going to be using the cubic meters as they are. So meaning to say, if this is P1, we're going to use V1. All right, so we're going to use P1, V1, which is equal to this whole part. So we are going to take this formula, or we are going to use this formula in terms of MRT, because we have the mass there. Remember, the mass, we have it. So you can use this one also, which is one and the same. Or we can use the first one. So if we take the first one, it's going to be P1, V1, in this case, from the initial volume. If you use this, you're going to take the mass as it is. So I want you to prove with this one. So I'm going to use the first one so that you work with the second one and see if your answers, they are corresponding. All right, so from the first one, we are given that the work done is equivalent to P1, V1, into n over n minus 1. This whole part is going to be P2 over P1 to the exponent of n minus 1 over n minus 1, like this. All right, so that is it. We are going to have our work done in this case. Taking the initial pressure, which was 103, if not mistaken there, that was our initial pressure. Remember P1, when we talked about P1 here, 103. All right, so our P1, which is 103. So we are going to have 103 times V1, which is the volume at the inlet V1, we have a part that is got V1 here, all right, on our calculations. All right, we never calculated V1, so it means we are supposed to calculate V1. All right, let's get back to our relationship. Remember, V2 is equal to 1 over 6 of V1. V2 is 1 over 6 of V1, and we've got V2 here. All right, so this one we are forced to calculate V1 now because we do not have this V1. But from V2, we said V2 is equal to 1 over 6 of V1. So if you multiply by 6, it means 6 V2 is equal to V1. So 6 times V2, which is 0.137, is going to give us V1. So our V1, if you multiply, we are going to obtain 0.822 cubic meters, all right? So that's we've got V1 in this case. So here we are going to multiply by V1, which is 0.822 times. Remember, N, we calculated our N, we got 1.21, guys. Okay, so I'm just going to write this 1.21 over 1.21 minus 1. Then this whole part into P2. Remember, P2 was at 900 kilopascal, all right, over P1, we wrote it before here, that's 103, everything to the exponent of N minus 1. Remember, our N is 1.21, so it's 1.21 minus 1 over 1.21, everything minus 1 like this. All right, so that's it. You have to apply direct as it is everything properly on your calculator. So that was going to give us the work done in this case, which was going to be 222.81. That was going to be 8187 and so forth, which is going to be 9 in this case. All right, in kilojoule per kg of what? Per kg of air in this case as given from our question. So that is it. As you can see, in order for us to have the work done, we needed to obtain V1 from our V2 ratio, the one that we are given, the ratio between V1 and V2. We calculate the value of V1. With the value of V1, you have to substitute it into your formula, and also to take note here that the work done was needed in per kg of air. So it's supposed to be kilojoule per kg of the air. So when you are dealing with compressors, guys, understand your question revise back your gases there, the law of gases, thermodynamics of gases, revise back that part. It's very, very important to do that, as it helps you to manage to connect the formulas. How we're using it before is the same. So we just have to revise back again. That can help us a lot. But for now, that's it till we meet again.